Okay, so I would like to welcome everyone to this seminar. Some more people are joining now online and also physically. It is my pleasure to introduce you to Eduardo. Eduardo is a PhD student at University of Padua in Italy, and he has been visiting my research group in the last 7, almost 8 months now. Yes, and we have been working together on several different aspects of computing continuum, and he will talk a bit more about some of the things that he has been working on. So without further ado, I would like to leave the floor to Eduardo.
So thank you, everybody. Thank you all the people here, of course, and also online. Again, if you have questions, feel free to interrupt whenever you feel is appropriate and the case. Basically, today we have potentially 2 sessions. There is an initial seminar in which we are, at least I am going to talk with you about a vision for a runtime infrastructure capable of spanning, of course, the cloud edge continuum. Then we are going to see what these terms mean. But this is just in the first part. There is then this hands-on section for those willing to attend. That will be, I mean, we're not obliged to do it, but like it is a hands-on session in which we will try some of the technologies that I'm proposing actually in the first part of the seminar. So I think if any of you would like to attend that second part, and then of course there will be a little break between the two, and we will be synchronized at the time. So that being said, I think it's good to start with like a reflection or a recollection on what actually cloud and edge means, just to be sure that we are like on the same, we're using the same language. So it's, what is the cloud? That is the first question. Like we think about clouds, I think like in an historical way. Like I like to think about how did the cloud actually came to be. And so basically that was the case of companies that has a lot of physical appliances like physical server with a lot of capacity. And of course, like usually on average, systems do not require to use it all. It was just viable in case of some spike in performance or some spike in performance, things like that. So basically, many companies in the US in particular found that have a lot of spare resources, and these spare resources could actually be used and potentially put to fruition if they rent somehow to other people. So in a word, like we can say that the cloud is composed of spare resources, basically, gather and offer as a service. But what are the key traits of this computing model? Thinking about how do we access resources in the cloud. We usually see that we can access them often through web level protocol. This is often the case for many service, like think of probably LOS 3, I guess, in Amazon Web Service, for instance. Those resources are actually pulled together, meaning that a lot of little resources that are available within a data center are actually pulled together and offer as a sort of a single aggregate, on top of which virtualized resources are offered. So I think the 3 key elements of the cloud model are basically that. So we have resource pooling, meaning, to say it like more clearly, fragmented resources that are grouped together into one single sort of federation, and then virtual resources that are offered to customer in some way. And the means in which or the channel through which we access those resources is basically a web level protocol. We don't usually access those resources, for instance, using sockets or things like that, generally. Now, in the cloud model, we see that basically the main actor is the infrastructure. Infrastructure is the ruler, in a way. Everything depends on the infrastructure. Service can be moved and can be handled entirely depending on that. The application actually is quite oblivious of what happened underneath. So we think about any virtual machines that we can run on some cloud provider, we truly have very little control about what happens under the hood. The service can, like the application, is completely separated from the infrastructure. That's the main thing. And that's a lot of advantages, because if we think that the infrastructure underneath may be very heterogeneous, maybe scattered around the globe, maybe whatever, but the application has no knowledge of it and just rest on top of the infrastructure, which is a definitely interesting property. So when we think about cloud computing, we have, I think, some advantages that are pretty interesting. So accessing things through the web is good because using web level protocol, we can basically identify resources that are everywhere in the world. Like we have identifiers, and we can name objects that are everywhere without any information about their physical location, which is a very cool property. Think if we had to use, for instance, an IP address, meaning that if a service should switch from one node to another with a different IP address, then we should reroute our traffic, which is not the case on web level protocol. And this is a very interesting property. Resources are virtually infinite, meaning that when we have to use sources in the cloud, we don't really have any limits, like no upper bound on how big our machines can be, literally, apart from the cost of it. And then all these two things make componentization very natural. So when we have shared protocols that everybody uses, in this case, web level protocols, and when we have a sort of a very homogeneous infrastructure, because we don't know what the true infrastructure is, then we can think about building container or virtual machine, or in general, we can think about fragmenting our kind of monolithic application into a lot of little components. This is another very interesting property. But we all get all of this at a cost. And the cost is that basically abstraction tend to be costly. And we lost a lot of control on the infrastructure, meaning that, again, we have no idea what's happening underneath the application. Right. And when I think about abstraction cost, think about, for instance, containers, which is a standard technology developed mainly for being used in data center or cloud resources that actually has a certain memory footprint. So can you imagine like running a container in very, very small devices that like virtually may have not even as operating systems? Like very difficult. They are pretty costly abstraction in a way, much less than virtual machines, but still pretty costly. This was just sort of a sketch. What is the cloud? Now, the other question is, what is the edge? And basically, the edge is sort of the space, the computing space, if you want, or basically that set of devices that has some physical component. At least this is the definition that I like the most. There are many and various, but I think this is one makes it's pretty clear, straightforward. We have physical devices around, meaning that when we have physical devices, we potentially can do very interesting stuff. This is the realm of embedded software. So we have software that run on machines, on computer that are embedded on, for instance, some other physical appliances. They move mechanical arms, or they are within cars, things like that. So we have potentially a great control of the world, like of the machinery connected to those onboard computers. Potentially here, also we can think of running real-time computations because we have control of everything. In a sense, we see that the application takes control of the infrastructure. Now, conceptually, this is the standard for many embedded systems. Think about, for instance, flight control systems. Can we consider them embedded? Yeah, definitely. Then we have all the software required to move the vehicle, or the vehicle in this case, within the software level. And the software is developed for a specific board. There is no possibility, or like it's not very easy to move the same software on another board because the software, again, takes control of the infrastructure. And then in this case, which is somehow opposite to the cloud one, we see that the true ruler is the application. Application do everything. This has some advantage, of course. We have potentially a very fine-grained control about the execution. We know everything, what's happening, what is not happening, what should happen potentially. Abstraction potentially are very low level, meaning that they potentially may be very well performing. But we have some disadvantages also. And the thing is, basically, this sort of application tend to be generally monolithic. Think again about, like any embedded application, and actually it's very difficult to decompose it in component. And there is not, like in the web lab case, a sort of standardized way for getting communication from component. One very, very, very extreme scenario, consider, for instance, times and space partitioning system. When we have like hypervisor that strictly federates the timing resources for instance, some application running within those time slice. Then getting communication going through, it's pretty complex and is far way low level than can be on top of the web and all that nice protocol we have. Another disadvantage or drawback is that maintenance usually happens offline, meaning that it is very difficult to touch the software once it is operational. So if we have a like embedded application running on a certain node, it's very difficult to make modification to that for whatever reason, without, of course, having to flash scan things. And this is a great disadvantage for a system that is truly operational. Now, this was just to give you, so if you have any question, of course, feel free to interrupt. But the point of this was just to give like at least a visual standpoint on what is the edge and what is the cloud. They are different, but like modern application probably need both. Now we see that we have tendentially an increase in the expectation for functionalities in the very edge of the network. I do like thinking about the automotive industry, just because recently I was in a German car, and it was super fancy. There were a lot of things. There were a lot of display, a lot of things going on in the car. This is definitely a sign of a trend, and we definitely expect to have much more functionality in those vehicles now and in the future, compared to my car that has, unlike me, almost 20 years now. So we need the computing power that the cloud can offer. And we need also to use probably something else, because we have our real-time computation that cannot be delegated to the cloud, which is pretty far from the physical world. Another trend that I find particularly interesting is that regarding internet service provider. Now, I was recently talking with another researcher in network communication, and he basically told me things that I find very smart, was that nowadays internet providers are becoming communication service provider. Now, the terms are a bit misty, but I do think that they pass the message that people that own, like companies that own like internet service, they offer internet service, they have physical appliance, of course. They have switch, they have router, not exactly router, but they have an infrastructure in which potentially they can host part of the computation. And they are moving toward this cloud model in which part of those resources can be effectively used for performing some form of computation, which is very, very interesting. And also means that the cloud is in a way getting closer to the physical world. The thing is that modern cyber-physical systems then need both. Again, we need the cloud for doing a heavyweight computation, things, for instance, training machine learning models for whatever reason, or any things that involve analyzing large amount of data. Those things will it's very counterintuitive that they are running such heavyweight computation in the edge. Conversely, we need the real-time, we have time critical components that need to run in the edge. For this reason, we are basically looking for a solution to integrate both the cloud and the edge into one single model. And the thing is that both cloud and the edge by themselves are not really enough. Again, clouds suffer from having very heavyweight abstractions and very high footprint. So can we run container again in very constrained devices? I guess probably not. Do we want to switch to the edge model and have again those monolithic application that have absolute control of the infrastructure at the price of no possible way of scaling up or down. This is clearly not very appealing. We need a new model, in my opinion, and a seamless model that is capable of allowing computation to run in both the edge and the cloud. And that's the idea of an edge to cloud continuum. Okay. Well, sorry, something not working in the presentation. Yes. So this is basically the idea. The idea that we want to be able to use both. We need the cloud and the edge for modern cyber-physical application. We start thinking then how to build this runtime infrastructure. Now, I think it's good to spend a few minutes about the term infrastructure. I'm thinking about, in this presentation, we are going to discuss about software infrastructure, meaning the software that run on top of this physical infrastructure, if you wish. So maybe it's a bit misleading. In the previous slide, we mentioned about the cloud infrastructure, like the machinery that is there. And this is one thing. We are going to talk about the software level. If you want, we're going to discuss about a runtime environment. Just to be clear, that you get no surprise in the middle of the presentation. So we think again about building this software infrastructure. And this time we start from the edge. In the edge, again, we have devices that interact with the physical world. Thinking about sensing and actuating, for me, is very natural. But again, the physical worlds do change. Does change, at least. Things, for instance, move in space. This is pretty obvious in some context, like the automotive one. And more generally, the question that I would like to ask is that, do you think that location, for instance, impact on computation? And well, I think it does. Like considering the case, for instance, of machine vision application, this is a very, I think I like it as an example. This is all those these algorithms that try to do, for instance, object recognition, do have a concrete benefit of course, computing closer to the target of their investigation. So this is an example of computation that should run in the edge, because of course it's very hard to do object recognition in the cloud, meaning that you would have to do a stream of all the data up to the cloud. Maybe this is not desirable or possible in certain conditions. And it's very clear that performing object recognition close to the target improves the performance. From this and from other example comes to us the idea of that maybe some computation should actually be allowed to move and relocate in the physical space. In response, of course, of changes in the world. But can they, like, thinking again about our edge model, can we move computation at least easily around, or not easily, around once the deployment is done? Doesn't seem the case. If we have our application that performs some machine vision inference on a specific device targeted for a very specific board, it's tough to migrate all the software for running in another device without even thinking of doing it after deployment and in real time. This go against the practice that we currently see, at least in embedded development. So in abstract, what would we need to perform this live migration? So a migration is somehow capable of preserving the advancement of the computation. I think there are three ingredients, at least. And I like the first sentence, like build once and run anywhere. Now, probably someone will point finger to Java. I'm not talking about Java. I'm talking of another bytecode, but we are gonna talk about that later on. But this is, of course, a prerequisite. If you are not able to run the same application components, once, of course, we have compiled it or built it in another node, there is no point in migrating, right? If we have our application, we have compiled, like build, say for ARC64 target, and we want to run in an ARC32 or something else, so like x86 targets. No way, we need to build it again, unless we use a bytecode or something else. So we need a way to build some mechanisms that allow us to build our components and then run in any node. Then we have the things about resume and restart, meaning that we really do not want to have to restart the application from scratch when we move it, because otherwise we will incur in a very high penalty at trial time, meaning that if every migration required to re-execute the things, then its potential advantage will be really hindered by that fact. So we want to be able to to resume preserving the state of the computation. Ideally, we would also need some form of isolation. Now, isolation usually happens against different axes. We are going to talk about maybe later on about that, but the thing is that we need a mechanism to be sure that those migrating components execute somehow in an encapsulated form without causing too much interference in the system that is already running below those. So we need some mechanism for isolation, but we are going to discuss about that later. There are many technologies that I think can potentially be used for that, but there is one that I like particularly, and that is WebAssembly. WebAssembly, it's interesting. It's a bytecode. Was built. It is basically maintained by a community of companies and developers, pretty large in a way, and has a very curious origin. It's actually a technology that, as the name says, was born and developed for running embedded, but in a browser. This is part of the web world, if you want. It was thought, it was developed in the beginning with the idea of making sort of backend or like some computation running within browser more performant than the corresponding JavaScript-based approach using Node or things like that. So it was things for sort of giving a little acceleration to some operation coming from web page, basically. And of course, they have to define a standard was performant enough to compete with native execution, and that can potentially run entirely encapsulating what in WebAssembly speak is said to be a sandbox, meaning an environment that is completely confined, so that a component that is actually downloaded from a web page can run without being able to touch the memory of the main system or outside of its little pool of resources or invoking any function or system API that may cause damage in the overall system. But nowadays, kind of moving towards the edge. The good thing is that we can take programming language like C, like Rust, or things like that, compile them and build them in WebAssembly bytecode, and then potentially, again, using the interpretation or just-in-time compilation, run it directly on top of a variety of devices. Really a variety, like wherever there is a WebAssembly runtime, potentially we can run that computation, which is a very cool property, meaning that already this is truly a mechanism that allows us to build once and run anywhere, potentially. And the requirement for supporting WebAssembly bytecode are pretty simple. So they are not very demanding. Someone may ask then, what's the difference between WebAssembly and Java? This is often a question I receive often. The thing is that the bytecode is truly very simple compared to the Java bytecode. And while Java was built as a language, potentially like a system language to build entire application, WebAssembly was designed with the idea of running just little embedding. And for instance, I think it's not, maybe in the hands-on session, we can go a little bit more into the instruction set of WebAssembly, but it is truly very simple. And that's, of course, make it much easier to study, to analyze formally, and see what's happening under the hood. Of course, running in a little sandbox is not that interesting if it's not possible to interact in some way with the overall system. Now, the mechanism that WebAssembly uses is the WebAssembly system interface. It's not too interesting to go into the detail, but it's basically a mechanism that allows a WebAssembly module to interact with the external environment. So there is a standard, and this is something that can be done without re-implementing the entire runtime. The thing is that now we potentially have a solution that seems apt for building ones and running anywhere. The thing is that can we, in some way, also introduce a mechanism to perform a line migration? So can we use WebAssembly for running a little bit in a node, stop, move some form of state to another node, and then restart or resume from there? That's the question. So we have been working on a checkpoint and restore mechanism or procedure to be injected directly on the bytecode. And actually, this is an interesting thing to be done, which, oddly enough, the intuition for doing these things comes from a very, very peculiar embedded context, which is that of energy harvesting systems. I'm not sure if any of you is familiar with that system. See some people? Okay. Basically, energy harvesting systems are embedded systems that usually have no batteries. Maybe they have little capacitors that can store a little bit of charge, but no more. Think about, for instance, not the component, the chip, or like the systems that run on a satellite. Maybe, or not even, satellites or a little rover walking around in Mars, things like that. When, of course, you don't have an energy grid, you cannot plug somewhere. There's no way to plug. So you need some mechanism to acquire energy, to harvest it from the environment. And that's the point of energy harvesting systems. The problem that this system faces is that, think about as an energy harvesting system that uses solar panel. You have all the energy you want until the sun goes away. And when there is a cloud passing by or something covering your solar panel, even for a little bit, the system shut off. And they had a problem. Like, how can we develop a mechanism to restart the computation without having to start everything from scratch? Because otherwise, if we are unlucky, we can be very unlucky, and potentially the computation may never actually progress. So they have developed very interesting solution to do this, and we take one of those and we basically use it in WebAssembly. And it's very interesting actually. The idea is that we can take the bytecode, we can partition it into region. And we do this in a non-programmatic way. So the partitioning and the checkpoint injection is not done by a programmer. It's done by an algorithm, basically. So according to some criteria. And that can be done at compile time, statically. So we can think about taking the bytecode, chop it into regions, and then inject those procedure to perform checkpoint and restore in some specific point at the end, in particular, of those regions, which is interesting. These allow us to perform potentially a line migration of WebAssembly. So we are able to run our computation a little bit, stop, maybe at in the intersection of those regions, save the state of the computation. Now, I'm not going into the detail of what it is to say. We can see it later if you're interested, or if we want, just ask about it. But we can save it at that point, and then move state and computation to another node, and from there restart. This is doable, which is a good thing. Now, thinking of our system view, we have to think about how to run those computations. And the real-time theory will tell us that there is a good solution for handling requests that come periodically without a fixed period to our node, or better, real-time to our node, to our core, we may say. And this is the case of sporadic server. Sporadic server are basically a mechanism for executing incoming aperiodic request on CPU, and has two main advantages that I think are very cool. The first one is that it grants a form of temporal isolation, meaning that the interference that the sporadic server will cause on another task is bounded, and it's bounded in a very simple way to compute. So we are pretty sure how much interference we are causing while we are executing those incoming computations. The second thing is that it is bandwidth preserving. meaning that when there are no requests to be executed, it actually do not consume any CPU time, which is a nice property. Again, we can use WebAssembly also has this mechanism of sandboxing. We have not gone into the detail, but it's actually able to provide some form of isolation, at least from the host interface and from like spatial isolation, if you want, from memory area of the host. So we have potentially a mechanism that can grant like temporal isolation through the use of a well-known like real-time approach. Now, I'm using sporadic server thinking about a fixed priority scheduling, of course. This is the classical things. If we want to think about say a scheduling context with where the priority are not fixed, then we can think, for instance, of using like constant bandwidth server. There are many other options for that. This is not, of course, mandatory or compulsory in any way. This is the approach we are using in our proof of concept. But is, of course, there are many other scheduling strategies, just to be fair. And that's the point is we need temporal isolation. And we can do this through the scheduling policy. We can use WebAssembly to grant isolation from host interfaces and from the memory space. It seems pretty good potentially. But then we have a problem. The last one potentially, which is like how to coordinate the computation. This computation will move potentially, but then how to decide when and where. We need an orchestration strategy. And for the edge, no less. So we thought about what we have found as a two-level orchestration strategy. Now think about that. There are like some decisions that belongs very specifically to the application that is running. So I think there is a picture later on, but try to imagine like a system in which we have multiple applications running. Each application composed of an aggregation of computing service. Of computation. Yeah. So we have an application made of many computations. We want to schedule, or we want to execute multiple applications on our infrastructure. And of course, we have to grant that the application level decision of taken in one application did not affect anything in the other applications, meaning that the coordination of the computation within the application boundary has to be isolated with each other. So what's the point of this? Can we use, for instance, the cloud approach of using like one orchestrator that take care of everything, while granting isolation between different applications? I think this is not the case. We see that we have two levels of orchestration. One that is the infrastructure level, which means how we assign resources to application. The one that is application level, meaning how we coordinate the computation within the pool of resources that the infrastructure has allotted us. So this is very interesting, I think. Hopefully this picture is clear, or maybe not, but the point is that you see that we have two layers. The bottom one, which is the sort of infrastructure orchestration, meaning we want to assign some form of computing resources to application. And on the top part, you see application, the level of the application level decision, if you want, meaning where and how we coordinate the computation within that resources. And I hope you can appreciate that this clear, the graphically clear distinction between applications. So we have to be able to distinguish between application level decision of different applications. So if you are using, I'm trying to remake, to say again, like what I was mentioning earlier, like imagine to have just one orchestrator, they take care of all the computation for all the devices, like for all the infrastructural nodes that we have. Can you imagine a mechanism to isolate temporally and like to make some prediction about the response time or like the timing required to perform any decision at the application level? That will be terribly complicated, more complicated. And now think about what does it happen if one application adds, for instance, another computation within its pool. If there is no isolation, then we have to recompute a sort of end-to-end analysis of all the system, which will be very, very tragic. That was the idea that we have been working on regarding our two-level orchestrator. And this actually opens up a lot of possibility. Now, once we have distinguished between the infrastructure level and the application level for the orchestration policy, then we can think, we can explore a lot of possibility regarding the application level orchestration. In particular, here we have the work and looked for a solution that was actually capable of run entirely in an entirely distributed manner. And we found that a particularly interesting algorithm to do this is this alternating direction method of multiplier. Now, the name is complicated, but like the algorithm is even more complicated. But like we cannot, you can trust me that it works. This algorithm, I think, has a few characteristics that are very, very, very interesting. The first one is that potentially it handles the problem of deciding where to migrate as a consensus problem that we can model as an optimization algorithm. And we can potentially solve it in real time, in a bounded amount of time, which is, like, of course, very interesting if you are planning of running the thing in the edge. It has another interesting aspect that using this model, potentially we can decide to keep local data truly local, meaning that we are not obliged to, we have no centralized potentially, we can implement it in various manners, but one of those is one in which there is no centralized component that take care of sort of the control plane, but the coordination happen again in a completely distributed manner, where like there is no local data shared with all the cluster, and that is potentially very interesting. So I think we are almost close to complete now. I think this is the last slide. I think that the things that I would like to, the main thing that I hope it's best is that we can think about a software infrastructure to run computation across cloud and edge. We need both of them for different, of course, scenarios, because one is much more abundant in resources and the other is potentially much more time aware. We need to be able to move computation, though, at least in the very edge, because devices move in the physical world. Because we can have some devices that, for instance, are approaching shutdown due to a cloud coming on top of a little energy harvesting system, or maybe just for any other problem dealing with the physical, related to the physical world. Doing this require a mechanism to migrate computation, and we have seen that we can do this with WebAssembly, potentially. But then we need to be able to orchestrate them in a real-time manner. And that requires some form of isolation that require actually slicing our cloud-native orchestrator in a more time-aware fashion. Future things that we can do with that. For now, we are running our experimentation on top of nodes that use an operating system, but this is not a strong requirement. Like this is, why not trying these things on bare metal hardware? That will be very cool, but we require some more work. We'll do it in the next time. Like the other thing is about how about using this technology for running, for instance, other AI algorithm in the very edge of the network. Like once we are able to build maybe not a small or not so small model to WebAssembly, potentially we can run in any node that hosts our WebAssembly runtime, meaning that we can use that same technology also to fight the very heterogeneous environment that we face in the edge portion of the network. I think this was like, I think this is the end of the presentation. So let me know if you have questions. Otherwise, we can take a little break.
Is there any questions? So, Ali?
Yes, Eduardo, thanks for your presentation. This was very interesting, and it's actually very relevant with what we are doing right now. So we are also like using WebAssembly and think about kind of orchestration on top of WebAssembly. So this is, I mean, I couldn't listen to your whole presentation, but then the topic was very interesting. Maybe you can also, I'm not really sure if you, the VASP Cloud, because VASP Cloud is a kind of like distributed execution environment using WebAssembly. When you mentioned basically there where else can we run WebAssembly, and then how we can basically have this runtime everywhere in the edge, cloud, and even on the device. So maybe you can look at WASP Cloud if you haven't looked at that. But anyway, I just wanted to say this was very interesting. Thank you. And then I will write to you later with some, to share with you some of the work that we have done and see how much we have similarities.
Thank you very much.
Any other question or comments? No? Okay, then I guess that's more or less it for the first part. I mean, this was kind of a general introduction to the work that Eduardo has been developing in the past few years during his PhD. But he has prepared also this hands-on tutorial on some of these technologies, and he can show some more in detail some of these things. So he has another 45 minutes of this tutorial. So if you are able to attend, then you are more than welcome. Otherwise, this initial part is completed, and I thank everyone for attending.
Thank you.
Thank you very much.
No way of stop recording.